My name is Karthik Narasimhan. Good morning, everyone. I'm a fifth-year PhD student now at MIT, and my supervisor is Regina Barzilay. My work is usually in the intersection of NLP and reinforcement learning, and I'll give you a flavor of that in this talk. Most language processing tasks that we have right now rely on some reasonable amount of quality supervision. Take, for example, the task of machine translation, where the goal is to translate text from one language to another. And over the last couple of years, MT systems have increased considerably in their quality, and a big reason for this change has been the availability and the methods to make use of large-scale supervision. So we have large parallel corpora that we're able to make use of. Another task, let's say, consider that of reading comprehension, where the goal is to be able to answer questions based on certain passages. And here, recent research has shown that being able to have access to detailed supervision in the form of annotations of the underlying processes themselves can help considerably in being able to do well on these tasks. I mean, this is just an example, but there's tons of work out there. And so these data-driven approaches have really helped push the boundaries of NLP, but one problem with them is that it's often expensive and time-consuming to obtain these annotations, especially of good quality. And in this talk, I'm going to talk about an alternative paradigm where we can learn from reward-based feedback, and I'll show you two things. First, how we can use the framework of learning from rewards to be able to work with tasks where the amount of supervision is very limited. And in the second part, I'll show you how we can learn from weak supervision in the form of delayed rewards in order to learn good representations for language and semantics. So I'll be using the framework of reinforcement learning on a very high level. This is basically where an agent takes a sequence of actions and interacts with an environment and gets periodic feedback in the form of rewards. And over time, the agent learns from these rewards in order to take optimal decisions. So I'll go into detail later. So more concretely, I'm going to talk about two different projects that we did. The first one is going to be on how we improved information extraction using reinforcement learning. And this is joint work with Adam Yala and my advisor, Regina. The second part of the talk, I'll focus on how we can learn good representations for language and how we can use that to play text-based games. And this was work with Tejas Kulkarni and Regina. So let's first move on to the information extraction task. At a very high level, IE is the task of converting unstructured data in the form of, let's say, free-form text into a more structured form, such as a database over there. And over the years, there have been several challenges, and I'll just show a couple of them. One of the reasons that IE is so hard is that most of our systems which have been successful require lots of annotated data. And this is evident from looking at corpora that are normally used, such as the A's or things like Freebase, where we often have access to thousands and millions of entities. And such amounts of data are just not available for certain domains like medical or financial documents. And this is a very, very big problem because it's very hard for these models to generalize well with a limited amount of supervision. Even leaving aside the amount of data available, sometimes information extraction is hard just because it involves more complex reasoning. So if you look at this example over here, this is a news article on a shooting that happened in the United States, and we're interested in extracting entities such as the name of the shooter, the number of people who died in this incident, and let's say the location of the incident, and so on. And here you can see that inferring the fact that 6 people were killed from a couple and 4 children is not simply extracting this phrase itself, but you would need to perform some arithmetic and understand a couple means 2 and so on. So that's one thing. And if you look at the bottom part here, you would think that this person, Scott Westerhuis, who died in this incident, would actually be the victim of this incident. But if you look closely, he committed a suicide, and he's also the shooter. And this is something that you would need some non-trivial reasoning to figure out. So one thing we can do is obviously augment our IE systems so that they have this capability to reason. But let's look at some other sources on exactly the same event. So these are 2 other news articles. And you can see that the text is different, and it's actually easier to extract the same facts from these different articles. So in the first one, it's easy to see that 6 people were killed. And from the second one, the phrase Scott Westerhuis shot his wife and children makes it much easier to know that he was actually the perpetrator of the crime. So our goal here is to take advantage of this fact, and the main goal is to be able to extract from these alternative sources as an orthogonal direction of research. So where would we get this extra evidence? One place to look for would be the web, of course. There's lots of news agencies who put out online stories online, and we can search for them and get them. But this comes with certain challenges. The first challenge is that of event coreference. What I mean by this is, let's say we Googled for an event using the title of the original article. You can see that except for the first link, the other results that we get are also in shootings, but not the same event, even though they're shootings in Baltimore where 1 person was killed or so on. And this often makes it hard, and we need some mechanism to be able to sift through these irrelevant stories and find the stories which are actually on the same event. So that's the first challenge. Let's say we perform that. There's an additional fact that we need to consider. Let's say we have an extraction system which is able to extract from both these different articles on the same event. We would still have the problem where we could come up with totally different entities, totally different values for entities like the number of people killed or the location. And what we need to do is to have a mechanism which can basically merge these entities into a single set, which we believe to be the right one. So some of them might be incorrect. So we address both these challenges in an iterative fashion. So our approach is basically going to be in this format. We first take, let's say we get an original document, and we apply a black box extractor, a simple extraction system to get these set of initial entities. And once we have this, what we do is we have to query the web to try to get other articles. And over here, this is a decision that you would have to take on what type of query you want to do so that you want to get the right set of articles and so on. And once we get this, we will select an article from one of the results and apply the same extractor again to get a new set of entities. Now, note that, this new set can be a totally different one. For instance, you might extract, say, dad shot family, so the shooter was dad or something like that. And so our challenge now in the next step is to be able to reconcile these 2 sets into a single set, and that would give us now a set of entities which we believe in. Now we can stop there, or we can continue this process and keep doing this over and over again in an iterative fashion till we are confident in our final set of entities. And you can see here that this is inherently a problem where you have to take sequential decisions and decide to stop at some point. So this is naturally fits in nicely with the framework of reinforcement learning. So the way we formulate this is we have a sequence of states as a Markov decision process. And at each point, each state, a new article is shown to the agent. And it would have to take certain decisions in order to move on till it's confident. And in our particular case, we treat each sequence to pertain to a single event. So all articles about the same event. And at the end of this entire episode, we would have a final set of values we can then evaluate on. Cool. So I'll give you more details about the states and actions and so on in the RL framework. For the state, we make use of 2 sources of information. One is the current set of values we already have, and then the new set of values we've extracted from the new article. And along with these, we also assume that we have access to the confidence scores from the base extractor for each of these values. And given these, our state is basically a real valued vector. And it has the following components. The first component is just the set of current confidence scores that we have. And the second component is a set of new confidence scores that we have. This is so that you can this is to give information about the confidence of the base extractor itself in order to make a decision of which value you would like to choose. So in order to bias that. The other components are a binary vector, which represents all the matches between the two sets of values. A real value, which represents the similarity of the two documents themselves from which these values were extracted. So what we use here is just a TF-IDF-based cosine similarity. And the final part is a context vector, which looks at the words surrounding the values that were extracted in each of these different documents. Yeah.
How do you get those four things? Do you automatically do it for different stories?
So these four things are so you just feed in an article to a very simple information extractor, which has been trained on limited supervision, like some amount of supervision you already have, and you just get these four different things.
That you were interested in sugar numbers killed.
Yes, you know that the task is to get this. Yes,
okay.
yes, yes. The domain is defined.
Process it?
Sorry?
You collect all the shooting articles and then process it?
Yeah, so the assumption is you have a set of shooting articles. I'll show you more when we go to the experiments. You have a set of shooting articles, and then you would search the web for more articles and keep extracting from them.
So are you treating like the extractor as a stabilized model, and you plan to improve it development as well?
Yeah, so the extractor is trained once and never modified. Yeah, it's just a black box.
How do you decide like which article to read as like the new values?
So at each point, let's say first you extract from the original article, and then you have one set of values. And then now you extract from a new article, and that's the new values. And then you reconcile them. And then that is your current set of values now, and then take a next article.
How did you pick the new article?
I'll talk about that.
Okay.
And with the doc similarity, the current values are kind of aggregate of multiple documents, right?
No, the doc similarity is only the similarity with the original article.
Or the seed article?
The seed article, yes. Yeah. Okay. So I'll move on. So that's basically the state space. It's a real valued vector. So for the actions, which is related to your question, there's two different actions that you need to take at every time step. So over here, I separate them into a reconciliation decision, D, and a query decision, Q. The first decision that you need to take at every point is to reconcile these two sets that I talked about, the current set and the new set, into a single set of entity values. And we have a bunch of different actions you can take. You can either choose to pick one particular value of an entity from the new set and replace that in the current set of values. So that's either one of these different K entities that you choose. Or you could choose to take all the different entity values and just replace everything in the current set of values. Or you could just say, I don't want to pick any of the new entities and just continue. The last action is if you just want to stop and say, OK, I just want to produce the current set of entities as my final answer.
You don't allow picking multiple at a time because of like the power set problem?
Yeah, that's.
But can you do this sequentially? Do you discard the new at each? Like this picture makes it seem like you discard the new extraction, so you can't like go back to it.
Yeah, that's one thing. Yeah, so you can't go back to it in this thing. That's an ideal way to solve this would be if you could choose any combination of values. Yeah, but that would blow up the space. So that's the reconciliation decisions. The other decision that you also have to take in this particular state is to select the next query. And ideally, if you would select any natural language statement as a query, you would have an unbounded action space. And because of this, what we do in this work, we restrict ourselves to a set of different query types. And I'll talk a bit more on how we get these different query types. So our goal is to select one of these different query types, and then based on that query, the search and extract steps are pretty deterministic. You just search and take the top link and that has not been seen so far, and extract the entities from that, and then you get a next state and continue this process. So the queries themselves, we have a set of templates which are induced automatically, and the way we induce these templates is by using the title of the original article along with a set of words which have high mutual information with the gold values themselves. So if you see the second line over here, words such as suspect, shooter, and arrested are words that often appear around the values of the shooter, name of the shooter in the training data. So this is all done automatically. And then we get a bunch of these templates. I think we used around 5 or 6. And our goal is just basically to select among these different query types at each point. So you can think of it as the agent is, if it's not confident about a particular entity, then it would choose a query which is likely to have these kind of words because it's easier for the extraction system to extract that particular entity. So that's the entire intuition behind doing this. For the reward, we just basically set it to be the difference in accuracy between the current set of entities that you had and the previous set of entities. So at every step, you would get a positive or negative reward depending on whether your accuracy is increased or not. And we also have a small penalty at every step. This is to make sure that the episodes are short and you don't have to query too many times. A simple way, a standard way of learning to maximize your expected reward in these kind of episodes is that of Q-learning. Just to quickly go through this, you have something called the Q function, which maps a state action pair to a real value, which represents the agent's notion of future discounted reward. And Q-learning can usually be performed using iterative updates. So at every transition, you can perform this update, which is derived from an optimality equation. And using a Q function, a simple policy can be just to select the action which maximizes your Q value at every state. So in our case, though, the state space is continuous, so we can't just have a sort of table for the different Q values. So we need to approximate the Q function in a parameterized form. And we do this using a deep neural network, which basically takes in the state as input and has a bunch of linear and nonlinear layers. And the outputs that you see there are Q values for both the reconciliation decisions as well as the query decisions. And so recent work has shown that this leads to some complications. You can no longer perform these updates at every time step as and when you get these transitions. This is because this would lead to some correlated updates, which would lead to instability in the learning. I'll show you how we can handle that. So here's the overall flow of the algorithm. You use the DQN to convert the state into a set of Q values. I only show you A as generic for D and Q here. Given these Q values, we take actions using an epsilon greedy policy, which is basically to take the action with the max Q value most of the time, but with the probability of epsilon, you just choose an action completely at random. This is to explore the action space more effectively. And once we do this, we can apply both the reconciliation as well as the query to get the next state, like I showed you before. Along with this, we get this reward, which is basically to say whether your accuracy is increased or not. And once we get this particular transition, what we do is we store this in an experience memory. So we don't use the iterative update directly. Once this transition is stored, we then sample a mini batch of transitions from this entire experience memory. And this avoids the correlated updates that I talked about, since all these different transitions are likely to be from different episodes, and hence the training of the neural net will be more stable.
For computing accuracies, how do you get the ground truth? And how do you know what the correct answer is?
So during training, we have access to the gold entities, right? And so you have access to the gold entities, and you have the original article. But your base extraction system might not get the gold entities. But then you can look at other articles also, which you don't know whether they actually belong to this event or not. And then you look at the final set of entities and compare that to the gold. So you do have access to gold entities during training and during testing too, which is basically used to evaluate the system.
How many articles contain the exact ground truth out of however how many you're training?
You mean the extra articles, or?
So when you extract those 4 items
Yeah.
from each article and each state, how many of them exactly contains the ground truth? They're very accurate.
So the original articles, all of them contain the ground truth. But the extra ones, I don't have a number, but some of them are completely articles on different events, and that could be misleading for sure.
I see. I wonder how much noise there is.
Yeah.
Given some shooting articles are consistent. It's such a big shooting. There's only one event in the city for that entire month.
Right.
You will just get the right article again and again and again.
Yeah.
Whereas others, like the one you showed, it may not be the case. But I don't.
Right. So I can talk a bit on that when I show you the baselines, and they will exploit the whole set of articles, and they're much worse. But I'll show you that. That's a good point. So once we have this batch of transitions, we can perform a parameter upgrade of the neural net itself, and this basically these gradients can be easily derived by trying to match the Q values that the network produces with what is expected from the Bellman update. So that was basically the training part. Now I'll show you some experiments that we ran. We used two different data sets where it would be easy to find redundant sources of information on the internet. The first one is on mass shootings in the United States, which I used this example. The second one is that of events of adulteration that happen around the world. And we got events from the Food Shield EMA database for this. So you can see here that the number of original articles for both cases available for training is pretty low. It's in the low hundreds. And one thing to note is that so the black box IE model that I've talked about, the base extraction model, has been trained only on the train source articles, and the DQN is trained on only the train set using both the source and the downloaded articles. So I think even though we get more than tenfold downloaded articles, a lot of it is junk. I don't have an exact number, but. So for the base extraction model, we played around with Maxent and CRF, and finally converged on this, which is basically a Maxent classifier which uses the context words in order to classify each word and label it as either a shooter or a number of people killed or nothing. And once this is done, this labeling is done for all the words in the document, we choose the value which appears the most for each entity and use that as the document level annotation. We used a bunch of features, and these features were tuned on the dev set. So I'll show you three different types of baselines that we use. This might give more insight to your question, Bean. So the first one is a simple reconciliation system, which is basically the first type of system chooses the entity value, which has the highest confidence from the base extractor. And the second one just takes the majority value extracted from all these different articles. And we make sure to filter the articles using a threshold on the TF-IDF similarity, which was tuned on the dev set. The second type of baseline is slightly more involved. Instead of taking all the articles after this threshold, what we have is a meta-classifier, which has more power in the sense that it can make the exact type of decisions that the RL agent can make. So given this exact state as an input, at every stage it can decide to take either a specific entity, take all the entity values, or take none of them. And we then get this for all the extra articles and then aggregate them in one shot using a confidence-based aggregation. Basically take the entity values which have the highest confidence. So basically this is a more filtered form of baseline. The third one is just an oracle, which assumes that you make perfect querying as well as reconciliation decisions. And this is an upper bound on any RL agent which performs this task. So for the RL models, we just had three different ones. One which does basic only reconciliation decisions. It has no power to query for new documents. For this, what we did is we presented all the documents from the different query lists in a round-robin order, so it cannot pick and choose. The second model can do the reverse. It can choose which query it wants to look at next, but it cannot perform reconciliation in the same way that I talked about before, and we just use a confidence-based aggregation there. The final one has the freedom to do both these decisions, and you'll see why it helps. So here are results on the shootings database. So the first four bars you see are the baselines, the base Maxent model along with the baselines. You can see that the baselines don't really help. The base aggregation systems don't really help. And this is likely because of the long tail of noisy articles that we have. And you can also see that the RL system is much better, and in most cases, almost halves the gap between the baselines and the oracle system.
So just to make sure I understand, so the intuition that the sequential model is better is it's avoiding a lot of noisy articles that are confusing the baselines.
Yeah, so it gets to pick which type of query it wants to do, and also it stops pretty early. It doesn't, so since there's no threshold, so TF-IDF thresholding works to some extent, but you would still have a lot of documents which may be like a shooting in Baltimore, but a totally different one, but may have similar content, right? So there's definitely a long tail.
Could you remind me what is the oracle here? Because the shooter name, the oracle seems pretty limited.
Yeah, so here, the issue with shooter name is that our evaluation is strict in the sense that we need the last name as well as the first name. And we take like an F1 metric there. So some articles just have the last name, and then your score would be like lower because of that. And on the second domain, you see a similar trend, which is basically, again, you see that the RL extract model does much better than the baselines, and it's pretty close to the oracle compared to. So this graph over here shows you a comparison between the different RL ones, and you see that having the freedom to choose both these type of actions actually helps a lot. An interesting point here is that the query model doesn't do as well, and this is because the reconciliation part is much more important in the sense that you can always choose to ignore the entities and your performance won't drop. Whereas if you do a query, if you do a query type model, we still have a long tail, and we might switch entities from the original one. This is basically to show you the learning curve, where the agent slowly learns with more and more epochs of training. And you can see that the reward slowly shoots up till it converges at some point.
Your meta-classifier?
Yeah.
The feature vector it takes is previous state and current state together, just like your state of RL took.
Oh, I didn't mention that. So it takes the original article set and the new article every time. Since it doesn't have a state, so it always takes the current set to be the original and the extra articles.
Why not just an article in the label, and if you train on that, wouldn't it be able to classify the correct article contains all the right information versus not? Feature vector.
Since we don't know whether their article is related or not. We don't have access to that supervision.
You don't have that label.
Yeah.
Okay. Yeah.
But we could do that if we did.
If you have
Yes.
that.
It seems that there's a kind of a dip around 60 to 80 elements, and then it comes up again. What's going on?
Yeah, so the point there is, so the reward is an aggregated metric for all the different entity types. So what happens there, I think, is it's trying to improve its performance on city, and that sort of hurts it hurts it on the other entities. So since at every point you can choose which type of query you want, but the aggregation you perform is still on all the set of entities, you might learn to query better for improving performance on city, but then that might lead to a slight drop. And I think that's what happens in all the other ones go down, but the city one goes up. But then it learns that, okay, I can perform these set of queries to get all of them up.
Regarding on how you train it, the deep network, you mentioned that it approximates the Q values, and your like Y variable to train it was the Bellman update, like what of
From the Bellman update, yeah.
From the Bellman update, but I am confused regarding your action space. Are you running the Bellman update like the classical Q learning to get those Q values and train that reinforcement?
Yeah, so in the Bellman update, you have the Q values for the current state, and you also need the Q values for the next state in the transition, right? So we can get both these values using the same network. And in practice, actually, we use a target network. Those are details in the paper. But you get both these values, but then the recursive equation has to hold, where Q is basically R plus gamma times the Q of the next state. And that's what I meant by the gradients can be derived, because you're trying to only match the Q value of the current state. That is fixed. You don't take a gradient on the Q value of the next state.
You have your query templates. Do you have like one for each of the slots you're trying to fill?
Yeah, so what we did was one was just the title and one for each of the slots.
How many steps do you typically take before it stops?
Yes, so the RL extract model takes around 9.4, I think is the average. I can give you details.
How many slots do you have in your template to fill in? Or
How many different actions? Yeah, so it's 5 in this.
How many different attributes are you trying to find? So you have the shooter and the...
Yeah, so it's 4 different attributes, the 4 I showed you here. So in the first case, there's 4 different attributes, and the second one is 3 different attributes, food allergen.
Did you try using the timestamp of the articles to filter out bad articles, because that seems like
Yeah.
to be very deterministic?
Yeah, we set a range around the original article. I think the range was around 5 days, so that we don't get totally irrelevant ones. Yeah, we did it for all of them.
So this is a slot filling task, right?
Yeah.
How do other slot filling methods do with your data?
You mean like?
KBP, like could you run this on typical data sets for this task?
Yeah, you could definitely do that. We just used straightforward. So since CRFs work pretty well for slot filling tests, we tried CRFs and Maxent. But you could do this with any other model. And so the base model can be anything, and you could apply this on top of that because you're trying to get extra articles.
But the way you described that you said CRF over a single document, right? But
Yeah.
You're using lots of documents.
Yeah.
Like typical slot filling KBP evaluations, you have a system that will fill a single slot
Yeah.
using lots of documents.
Yeah.
And you're not comparing against any of those, but you're doing the same thing, right?
The difference is that you would need to know which documents are relevant to the same event, right?
The slot filling evaluation has to do that too. Like in KBP, you have to also.
You would do something like an IR system to retrieve the relevant articles and then do that. Is that right? As far as I know.
Like you find entities and then like you do an entity linking first.
Yes.
Essentially, and that's how you do this. Like
Yeah.
similar to
Yeah, you would try to find.
But right, it's the same task.
Yeah, no.
You're doing. Like it's both. You're given a corpus. You want to fill slots. And yeah, just like.
But it's slightly different. I mean, the entity isn't a named entity. I mean, the entity is the event. It's quite a complex structure.
It's
not like you're looking for the birthplace of X.
Yeah, it's not a specific thing. It depends on each event itself as an article.
It's quite a complex thing you're trying to fill slots around.
Yes.
But that's also true of the TAC KBP evaluations. I think the evaluation is exactly the same.
I thought it was more specific entities.
I think it's basically the same. You get a corpus of documents, they may or may not be relevant. You have slots that you're trying to fill. The actual content of the text will be slightly different because like the TAC ones tend to be more like you got a person name and then you have to fill in like a birthplace or something. So like you can actually look for that person name in the text to like find parts that are relevant. Whereas like here you might have to just extract over the whole document. But I think conceptually it's very much the same like input-output spectrum.
Yeah, the input might be slightly different because you're just given, here's an event filled by this document. And so it's slightly different,
Yeah.
but almost exactly the same.
Yeah, it seems like you could adapt those methods to work pretty easily. The TAC KBP methods, even if you had to.
So it'd be nice to see a comparison.
Yeah, okay, we can definitely try it. That's a good point, yeah. Okay. Okay, so I was going to show you some examples of where our system does better than just using a basic extractor. And you can see here that it is able to retrieve other articles and extract from them. And that's actually much easier to find the right values than trying to do it from the original article. And this is basically going back to the part I said where it might be easier to extract from alternative sources. So I've shown you in the first part how we can use reinforcement learning to handle tasks where we have a limited amount of supervision available. And this is basically something that is a viable alternative to improving IE systems themselves. In the next part, I'll talk about how we use RL to learn good representations for a language and use this to play text-based games. So for those of you who are not familiar, a text-based game is basically a game where the player does all these interactions with the world in the terms of free-form text, and you get a description such as this. You're standing very close to the bridge's foundation. If you go east, you will be back on solid ground. Bridge sways in the wind. And the player can then input a command such as go east, again in text, and then move on to a next state, which again is given in the form of a textual description. So these games were also called multi-user dungeons because they started off with dungeons, and they're predecessors to the modern kind of graphical games that we have. They still have a following though. So why exactly are these games challenging? The main reason is that you don't get complete access to the underlying state itself. Instead, you have to interpret and reason based on the text itself. So there's no symbolic representation available. And this is in contrast to like previous work. Just to give you a sense, Braunemann et al. In 2011 did this very nice work where they took game manuals for the game of Civilization, which is a strategy game, and they used these manuals in addition to learning from rewards to be able to play these games better. And they basically identified sentences which are relevant to the game state and used it to guide their action selection. So in this case, language was auxiliary and not essential. But in our case, our main question is, can a computer understand enough of the language and decipher what the underlying state is in order to play these games well? So in this sense of understanding, what I mean is that of actionable intelligence, and this is different from orthogonal from other approaches which look at semantics in a different way. So our inspiration basically is from recent research from DeepMind, which has shown how you're able to play games where the underlying state is hidden, but let's say you get input in the form of raw pixels themselves, which is a visual input, which is in parallel to the textual one. So in this approach, we're going to do two things. One is to learn how to take optimal decisions to play these games well. But in addition, we're also going to use the same feedback from the games to learn good representations for the text descriptions themselves. So we're going to do both these things. In a traditional RL framework, you would often represent these games as a sequence of states. Let's say in each episode is a game that you go through with. And at each state, the agent would have to take an action. And you often get delayed rewards. So you don't get rewards every now and then. You don't get rewards at every step, but only when something eventful happens in the game, like you level up or things like that. And one could use something like Q-learning if we have access to the state in a very nice form. But again, we don't have access to this, and what we see is just the text. So inherently, this is a POMDP, which is basically a partially observed MDP, where we only have the text serving as an alias for the underlying state variables themselves. And in addition to this, an important point is that the text may not contain all the information too. So even if you were able to perfectly parse it and identify the state, you would still have certain pieces of information that are missing. And this is usually to make it fun for humans to play. So one thing we can do is just use a simple bag of words representation to sort of give it more structured. But as we all know, that's unlikely to give us too much in terms of the semantics of the state itself. So in keeping with this line of annotation, one thing we could do is we could annotate the underlying state variables themselves and learn models which can convert the text to those variables and then operate on that space. But that, again, like I said, would take some effort in terms of annotating. And so in this, what we explored was, can we actually learn the representations also directly from the game feedback? So here's our model. We have two parts to it. One is a recurrent neural net, which maps the text description you get at every point to a vector representation. And you can then use this vector representation and feed it into another neural net, which is responsible for the control policy for playing the game itself. So concretely, there's these two parts. The bottom part we call is the representation generator. So you can think of each W here as a vector representation of a word in the text. And we initialize these word vectors uniformly at random. And we don't use like pre-trained embeddings or anything like that. So once these vectors are passed in through an LSTM layer, the output of this layer is fed into a mean pooling layer, and we get one single representation for the state itself, the VS that you see here. And then this VS is then passed to the second module, which is the action object scorer. And this produces two different sets of Q values, one for an action and an object. So what I mean by this is we restrict ourselves to commands, output commands, which have basically one action and one object in this work. So something like eat apple would be an example. So we get these different Q values, and our algorithm is essentially similar to what I showed you before. Given the description, we use the DQN to obtain these Q values, and then take an action using epsilon greedy for exploration, and get the next state along with the reward. And once we have these, we store them again into an experience memory and sample transitions for updates. So, yeah.
Are you assuming that you are given a list of options? Like, there's a description and then a list of these are the actions you can do? Or?
Yeah, so most of these games, since they're created by some developers, you can only do certain actions, like eat or walk or.
I remember playing one where it would just describe something and then it'd give you a prompt and you had to just guess at what you might possibly.
Yeah, so it's the same thing. You can type in whatever you want, but some things will just give you a response like, I don't understand that command.
But so how does your neural net handle this? How does it generate possible things from scratch?
Yeah, so here we have a list of commands that you can have, and it chooses from one of them. And if it produces a command which doesn't make sense, such as eat east, you would get feedback from the game itself saying, I don't understand that command, and that would be a negative reward for the neural net itself.
So you assume a given list of actions and objects.
Yeah, and the model has to learn which objects go with which actions, and when it has to perform certain actions, and when not to do certain actions.
Do you have any idea how you'd handle games that don't have any given list of actions and objects?
That's a good question. So G, who's sitting here, actually had some follow-up work where it was not restricted, the action space was not restricted to something as simple as actions and objects, where they actually had things like more descriptive actions that you could choose to take, and you would need to sort of choose between different choices. And there were like longer descriptions that you could take. Yeah, that's a good.
Yeah, so as Karthik said, I basically view these as two types of problems where you have the so-called natural language actions. The one is you are selecting from a pool of actions that are descriptions of natural language, and basically you could still try something like in Karthik's work, you can do some Q values and evaluating the utility by choosing a particular action. Well, another type of problem in this type of game is you can type whatever you want, and it's like generating a natural language response or generating a natural language action. And there, I think you could use some policy-based methods, like like in a dialogue systems when you try to generate a response.
Yeah, but it can be extended to unbounded actions in certain ways. But in this work, we assume that you have a list of actions and objects. So we can do the same thing as before. However, one issue here is that the rewards that you get are pretty delayed and very sparse. So one trick that we added was this of prioritized sampling, where instead of sampling uniformly from this entire experience memory, with the probability of rho, with the fraction rho, we sample transitions which actually had positive rewards. And I'll show you in the experiments that this actually led to a nice boost in the learning speed. So we experimented with this framework called Evenia, which is a very nice framework if you want to create your own mud games and deploy them. And we used two different worlds. The first one is a very small game that we created ourselves. This was useful to show the task itself and analyze the representations as the model was learning. And the second one is a pre-existing world, which we just took, which is an introduction world created by the developers of Avenia themselves. The smaller world is something we call the home world. It basically has 4 different rooms, and each room has a characteristic object. And the agent can get one of 16 different quests. The vocabulary is pretty small, and the descriptions are around 10 words per room. One thing to note is that if the agent enters the same room multiple times, it can get different descriptions uniformly at random. So we had multiple descriptions for each room. So one gameplay would look like, let's say we put the agent in the living room, and we gave it this particular description. The first sentence has a description of the room it's in, and the second one is giving it a certain task. So it has to go to a certain room and perform a certain kind of action in order to finish this game. And you can see that it would need to have some understanding of things it's not supposed to do and things it's supposed to do. You cannot just take a bag of words thing and try to just say, okay, I'll go to the bedroom and sleep in this case. So the agent can choose an action such as go east. It goes to the garden. It gets a different description of the room it's in. The quest remains the same. And it goes south and goes to the kitchen and eats an apple, and then it obtains a reward, which is delayed. So that was the first world. The second world is slightly more complex. It has more number of rooms and a vocabulary of greater than 1,000 words. And the harder part is that the descriptions per room are more varied, and this was because the developers wanted it to be challenging and interesting to humans. And you can see like one of the rooms has 100 different descriptions that can appear at every point, depending on the weather and things like that. So we used these 2 different worlds, and for evaluation, we had 2 different metrics. One is whether you actually complete the quest itself, and the second one is the average reward that you get. So you can get positive rewards for fulfilling the quest itself, but you can get negative rewards when you do something bad, like fall off a cliff or die when you're battling an enemy and so on. And in the graph that I'll show, an epoch basically would refer to training for n number of episodes and then testing on n different episodes and averaging that score. So for baselines, we had a random baseline. This is just basically to show that the task is not trivial and you can't just randomly find your way to the quest. The second type of baselines are basically the bag of words baselines I mentioned before. We took unigrams as well as bigrams. So here are the graphs for the home world for the rewards as well as the completion of quests. You can see first that the random agent does pretty bad. It doesn't complete even 20% of the quests. So you can't just randomly walk around and try to finish the quests. And you can also see that the LSTM DQN does better than both the bag of words baselines. One interesting thing to note is that it has a delayed jump. So you can see for the first few epochs, the bag of words models do much better. And this is because the LSTM DQN has to first learn a good representation for the text and then use that to bootstrap the control policy learning.
So you do mean pooling on top of LSTM, so you basically lose all the structure of the sentence, right?
That's debatable. So I mean, you can either, so there's multiple ways of using. You can either take the last output of the LSTM, or you can take mean pooling, which is basically doing some sort of equal weighted attention. And all these attention models work in things like machine translation and so on, which actually require the order of the words. I would say it's just like a very simple attention-based model where the weighting is equal.
Regarding the evaluation, did you hold out some quests as well, which you didn't train, and evaluate on those?
No, I think we randomly sample the quest at every point. Mm-hmm. Yes. So you would just get one of these 16 different quests at every point. Yeah. And so by evaluation, this is, like I said, at each epoch, you're just training on these random quests. And again, you would get n different quests at each point, and then that's the score you get averaged over them. Yeah. So this is as it's learning. On the second world, again, it's a similar kind of graph, but you can see that both the LSTM DQN as well as the bigram-based DQN learn to complete the quest 100% of the time. So one point to note, though, is that even though they both complete the quest, you can see that the bigram-based model gets a much lower reward. And this is in log scale, so this is significantly lower. And we looked at what it was doing, and we found out that, so this is a map of the world itself. What it was doing was when it was trying to cross the bridge, it often fell down to the ledge, and that would give it a very high negative reward. But it was managing to get back on the cliff and then keep trying till it reached the quest, the end point of the quest itself. So even though it was finishing the quest, the problem was it wasn't doing it in a suboptimal way. So hopefully this convinces you that having a good representation is actually essential, and this is something that would be very useful for successful gameplay.
So the layout of the map is fixed across all training episodes?
Yes. For this, yeah, it's a big world, and you would need to find your way to the final.
Is it possible that it learns the sequence of actions to optimal? Probably.
You mean just the sequence of actions you want to do? So yeah, one thing I probably should have mentioned is even though the world is fixed, it's a stochastic world in the sense that you can try to move east, but you can fall off the bridge still.
Okay.
So you're not guaranteed. So there's wind and things like that. And you can try to, you're not guaranteed the outcome of the next state. So this is not deterministic.
Sorry, I didn't quite get when you explained just looking at the figure, the bigram DQN has lower reward but higher quest completion rate, and you explain this because it's pointing to the dash.
Yeah, so the quest completion rate, both of them have around 100, and I think they move around a bit. But what is happening is the bigram DQN is completing the quest, but it's just taking much longer and falling down a lot. So it's doing it in a suboptimal way, whereas the LSTM one learns to avoid that fall and do it.
Do you have any intuition why bigram is more likely to fall?
So yeah, so the one thing that we think is because you get all these different descriptions when you're on this bridge itself. So the same state, you can get up to 100 different descriptions. And I think what the bigram DQN does is depending on the description, it would either decide to move left or right. And the more it dallies on the bridge, the more chance of it falling down.
Have you tried it in a scenario where your test word is different from your train word?
Yes, so I'll show you that. Maybe in the next slide, I'll show you that.
The map you showed us, I assume, is not visible to the software?
No, it's not visible to the agent, yes.
Have you considered measuring to what extent the software learns something like the map?
Yes, so I'll show you at the end that it learns to identify states which are nearby. But it doesn't learn an explicit map, but it
Sort of a local map.
It learns some sort of these states are close to each other. Okay. So we also looked into a little bit more of whether you need the action scorer to be very deep. And from this graph, you can see that having a linear model just at the action scorer is not as good as having a deeper model because it learns some more compositional stuff. This is basically a TS&E visualization of the word embeddings that we get at the end of the entire learning. So if you remember, I told you we just initialized them randomly from scratch. And you can see that there's these nice different clusters of the words themselves that the model has learned, each representing one of these rooms. If you see one of these, you can see words like grass, plants, and trees, and exercise, which are all words that were used to describe the garden and sort of actions that you would take in this space. And this one relates to your question. So what we did here is we took several text descriptions, and we took the representation that the DQN the LSTM was producing, which is the VS, and then we took the closest neighbors in this representation space. And you can see that the nearest neighbor is often either the same state or or a state which is either to the right or left, which is a very similar state, very close to the original state itself.
Are you,
Yeah, sorry.
how can you, so the top row bridge occurs in both of those, is it?
Yeah, so the bridge
How
itself,
it's not just doing some sort of word similarity thing.
I think it is doing some sort of word similarity thing. Obviously, the fact that the bridge is there definitely helps it.
So it's not necessarily learning something spatial, it's just learning similarity of the background or something.
No, I think it's doing both. So I think one of the examples is, so the first one is where you're halfway on the bridge and when you're at the edge of the bridge. So they're not the same space itself. But yes, it's doing both. It's using both the description as well as the state space, which is nearby because of the actions that it can take. So in both cases, it would like to move east, and that would definitely affect it.
The cliff is right next to the bridge, right?
The cliff is right next to the bridge, yeah.
But I would guess that you wouldn't get cliff and bridge to be close in this space.
So the bridge itself has 5 different steps.
Or like, just say the
Yeah.
nearest, the bridge state that's closest to the cliff. Right? So
Yes.
You said there are 5, whichever one is closest to the cliff, that's right next to the cliff, right?
Yeah.
Would those two, the description of those two states be close in this space?
I don't think so.
And that's Peter's clock.
I'm wondering if TF-IDF would give you the same result. It would detect the same kind of similarity. So it's not really, perhaps it's not really picking up on anything spatial.
Yes, I mean, that's true, because what we want to do is just get the underlying representation from the description itself. It need not capture something that's very spatial about the game.
But in principle, it could build a local spatial model by remembering sequences of events and saying, well, whenever I am here and I go east, I end up there. So those two things are nearby. Like they're one move away from each other. So it doesn't have to learn based on words. It could just learn the concept of things being one move away.
Yes, but I don't think we do that in that sense. Yes. So all this is trying to do is trying to map areas which have the same descriptions to the same space, so that it can perform similar actions.
So it's actually just a kind of a coincidence that things that happen to have similar descriptions are spatially together.
Yes, but if they were not, then you wouldn't be able to act well. But that's
So if I'm remembering right, it's been a while since I did RL stuff. Value iteration will give you an explicit model of what happens, what state I'm going to be in, given the action that I take in the current state.
No. So it would just give you the value of, so if you take the value of it'll just give you the value of a particular state that you're in.
Right, Q-learning does this. Doesn't value iteration give you, you learn anyway, if you could...
There's model-based approaches which could try to estimate what state, yeah, but this is model-free.
And in that setting,
Yeah.
you would build an explicit,
Exactly,
spatial model
yeah,
of the world.
yeah.
Just not in this. This isn't good.
Yeah, not in this.
Wouldn't you expect the nearest neighbor here to be an alternate description for that same location, or are you excluding that there?
I'm not showing that here, yes. Yes, so obviously the best one would be the same description itself, and then there's alternate ones. But I'm showing you ones where it's still the next state. It's not something that's far away. So I think this was a question that someone had. So we also tried transferring the representations that we learned to a different world, which basically has the same vocabulary, but the physical configuration is different. So the kitchen might be to the east and things like that. And you can see that it is able to learn faster when it has these bootstrap representations than trying to learn everything from scratch. So these representations kind of transfer to different worlds. And this is finally just to show you how the trick of prioritized sampling helped us. you can see compared to just sampling uniformly, both of them converge and learn to get the maximum reward, but you can see the learning is much faster using this prioritized sampling, especially in cases of the sparse rewards. So in the second part, I've shown you how reward-based feedback can be useful to learn representations for language, and this is sort of like a weak supervision task, which in the form of delayed feedback. So to basically conclude, I've shown you that reinforcement learning is a very viable paradigm that we can use to learn natural language semantics, and it can be used to reduce our dependence on large-scale, high-quality supervision, and for various different types of NLP tasks. And we have all our code available online, and if you have any questions, I'll be happy to take them.